Okay, good afternoon, everyone. Welcome to today's colloquium. Thanks for coming, and welcome to everyone who has joined us on Zoom as well. It gives me a lot of pleasure to introduce Darshan Joshi. I have known Darshan since 2014 when he was a PhD student at Dresden with Professor Matthias Weiter. He graduated from there in 2016. From there, he moved to Max Planck Institute for Solid State Research in Stuttgart, and then since 2019, he has been at Harvard working in Professor Sachdev-Ye-Kitaev's group. Darshan's research interests are quite broad, with embedded within the context of quantum phases and phase transitions in low-dimensional quantum systems, which include frustrated magnets, strongly correlated systems, topological phases, and so on and so forth. Today, he's going to tell us about strongly correlated phases in models with random interactions. And Darshan, please go ahead. And I'd request someone who has joined us on Zoom to please let us know if you can hear Darshan properly. So yeah, Darshan, please start.
Yeah, thank you, Sthitadi, for the nice introduction, and everyone here for coming to this.
Sthitadi? Hello?
Hi.
Voice is low.
Sthitadi, we could hear you well, but we can't hear Darshan.
Okay, can you hear me now?
Yes, well, yeah. Hi. Could you say something again, Darshan, please?
Yeah, can you hear me now?
No.
It's a little lower than...
It's very low in volume.
Okay, maybe do you have to adjust?
if you use the other mic, maybe, I mean, is that possible? Or the mic that Sthitadi is holding?
Right, I was actually using a handheld mic, but Darshan has one of these collar mics.
Okay, but can you hear me now? Am I audible?
I mean, you are.
You can use that. That's totally fine.
No, I think this small mic can be raised a bit up, right?
Yeah.
Ah, that's better.
Is it better now?
Yes, of course.
Yeah.
Okay. Yeah. No, it's fine. Yeah. Thank you.
Okay. Yeah, just let me know if I drop out, my voice goes down.
Okay, yeah, please carry on, Darshan.
Okay, yeah, so thanks Sthitadi for the nice introduction and everyone here for joining for this talk. So today I will be talking about strongly correlated phases in models with random interactions. This is something which I have been interested in the last couple of years. Before I begin, let me thank my collaborators, a bunch of graduate students at Harvard, some postdocs, Antoine Georges at Flatiron Institute, and of course my postdoc advisor, Subir Sachdev. So I'm a theoretical condensed matter physicist, and one of the very interesting aspects of condensed matter physics is emergent phenomena. So what do I mean by that? In the words of Anderson, more is different. So for instance, you consider two isolated electrons in a vacuum, let's say. Of course, they have Coulomb repulsion, same charges, they repel each other. So there's no way they can be attracted. They are just going to go away from each other. But you now consider a system of many electrons at low temperature, and in the right setting, they actually form superconductor. And the same pair of electrons, which in an isolated case would have repelled each other, in presence of many electrons and under the right condition, they actually form attractive interaction and these Cooper pairs, which then gives rise to superconductivity. So in my opinion, this is like the crux of what we do as a condensed matter physicist and what we are really excited about, that there are really some fascinating emergent phenomena that arises at low temperatures in presence of many body interactions. So superconductivity is of course a classic and very famous example. There is also a zoo of many body quantum phases of matter, starting from very conventional phases like ferromagnet or an antiferromagnet that you may be aware of. Then some slightly non-trivial examples like quantum Hall effect, where basically you take 2D electron gas, you apply some high magnetic field. What is observed is that instead of just linear dependence of magnetic field, your resistivity or conductivity is quantized in integer, or in some cases also fractions of integer. So this arises as a result of some inherent topology of your system. And another classic example that most of you might be aware of is Bose-Einstein condensation. So this also happens when you have lots of bosons at low temperature and they condense in the low energy state. So basically, there is a zoo of quantum many-body physics and quantum many-body phases. So how do we go about understanding these phases? And one of the key ideas is actually of quasi-particles. So if you have non-interacting system, then everything is extremely simple. You can just go ahead, diagonalize your system, get the energy eigenvalues, eigenmodes, and essentially you know everything about the system. Things become interesting when you have interactions. That's what the interesting stuff for us is. And what Landau showed was that even when you have interactions, to a reasonable extent, you can make progress by defining something called as quasi-particles. So these are nothing but effective low energy description of your system, such that essentially these quasi-particles give you a system with weakly interacting particles. These are dressed particles in some sense. So some familiar quasi-particles are, of course, phonons, which are quantization of your lattice vibrations in a solid. Or, for example, magnons. If you have, let's say, a ferromagnet, then you can quantize the slow-moving fluctuations of your spin or your magnetization, and these are magnetic quasi-particles, which are called magnons. So these are conventional quasi-particles, and these are conventional in the sense that you have some your degree of freedom or your constituent elements of your system, and you simply quantize them, and you get some emergent, and you get an effective quasi-particle out of it. But there are extremely exotic systems or exotic phases of matter that we encounter in condensed matter physics, which are these highly entangled phases. And what do I mean by that? And what happens in these cases is that instead of these conventional quasi-particles, you may have actually fractionalization of quasi-particles. So for instance, I gave an example of fractional quantum Hall effect. So here in the fractional quantum Hall effect, instead of an electron describing your system, you actually have quasi-particles which are fractions of your electrons. So for instance, in a particular case, when you have fractional quantum Hall effect with nu equals 1/3, you have this 3-parton construction, which effectively describes your system. Sorry, is there a question? Okay, another example is a spin charge separation, which typically happens in one-dimensional system where you have electron with a charge and spin degree of freedom, and these two effective degrees of freedom are actually separated out. You have a spin on and effective hole on. Another example, which is very, very interesting for condensed matter community, is a quantum spin liquid. So here you have fractionalization, for example, in a particular case in terms of Majoranas. So of course, at high energies, in high energy physics, nobody has seen Majorana, which is a particle such that its antiparticle is itself. So it's an antiparticle of itself. Whereas in condensed matter, actually, you can realize Majoranas, theoretically at least. There has been a great effort to experimentally observe them. But these Majoranas can emerge as emergent quasi-particles in certain interesting systems. So these are quantum spin liquids. So this is one category of highly entangled phases of matter. In an extreme case, you can actually also have a complete breakdown of quasi-particles such that this quasi-particle picture completely goes away. So for instance, you start with an electronic system, many-body interactions, and you find that there are simply no quasi-particles that can describe your system. And one prominent example of such a scenario is a non-Fermi liquid. So these are systems which are not Fermi liquid. Just like many other interesting systems, it's very hard to define such systems, but one of the characteristics of these systems is there are no quasi-particles. And some interesting things that happen in such systems when you have no quasi-particles is that you have unconventional transport properties. So for instance, you may have heard of a particular type of non-Fermi liquid, which is a strange metal in the context of high temperature superconductors. So there, in particular, what happens is your resistivity is a function of temperature, and it goes linearly in temperature. And why is this interesting? Is because if you consider a Fermi liquid theory, then your resistivity goes quadratically with your temperature. And this simply follows from Fermi's golden rule. But for this strange metal, it goes linearly in temperature. So it's highly anomalous. So why do we care about these highly entangled phases of matter? Okay, they are there in nature, or maybe you can realize in lab at some point. So what's the big deal? So the big deal is that, yep.
So no quasiparticles are unique.
Okay, so no quasi-particles translate into linear resistivity,
No,
or
not always. So that's why I said for a particular example
Okay.
of strange metal, it's linear.
so then does linear resistivity translate into no quasi-particles?
In general, yes, but there are some cases where you can have linear resistivity, let's say when you have electron-phonon interaction, and even in some trivial cases with disorder, you can have T-linear resistivity. But let's say in most cases, it does translate into having no quasi-particles, but one has to be careful in certain systems.
But in this electron-phonon coupled systems, which presumably at slightly higher temperature, the electron is not a quasi-particle in the sense of a Fermi liquid, right?
So I guess if you're talking about particularly bad metals, then yes, there are no quasi-particles there. But I think in some disordered Fermi liquids, you may have a situation where you can get a T-linear resistivity, although there may be some well-defined quasi-particles. So in bad metal situation that you are probably thinking about at high temperatures above the strange metal, sure, there are no quasi-particles there. So that's why I said, like in most cases that you would encounter, if you see a T-linear resistivity, like probably 99% of the times it's corresponding to no quasi-particles cases. But there are probably very subtle isolated cases where you may get it.
Okay, thanks.
Just following up on Shubhra's point. So if you take a metal and go to fairly high temperatures, actually, there's this phenomenon of resistivity saturation.
Right.
I'm just trying to recall, are there quasi-particles there in that?
No,
okay. No.
Yeah, but just to finish this discussion on this bad metal and resistivity saturation, I think it's not yet fully understood this saturation phenomena. So there are some theories about Mott-Farregal limit and so on, but I don't think it's completely a universal thing that people have observed, or one can work out a theory. In most metal, it does happen and saturate, but I think there are several examples where it just crosses this limit and never saturates.
I actually have another question. So what you presumably mean is that there are no fermionic quasi-particle. So, but it's a statement that there are no quasi-particles at all in the sense of no collective modes at all at low energy? Or is it only fermionic quasi-particles?
No quasi-particles at all. So there is really an extreme situation where there are simply no quasi-particles. So you are absolutely right. You can always ask the question that I start with an electron. Okay, maybe electron is not a good quasi-particle, but what about some other quasi-particle whose description I simply don't know of? I mean, there are probably hundreds of bases, infinite number of bases in which you can rotate your Hilbert space, and it's just that you are probably not working in the correct basis, and that's why you are not identifying the correct quasi-particle. You're absolutely correct, and that's why this field is in general very difficult to really pinpoint the case where you absolutely have no quasi-particles.
And how do you arrive at that statement?
Right. So in certain, let's say, well-defined situations, at least from a theory perspective. So that's why. So let's distinguish between the two cases, experiment and theory. So in experiments, it's of course very difficult because you are just given with an observation and you are trying to understand what that observation means, and there might be different ways in which you can fit it. But let's say from a theory point, we can make things even more clear. So you can ask the question, if I'm given a particular problem, can I conclude whether this the theory or the low energy state that I'm getting is indeed without quasi-particles? So there are different ways to do that. One is, of course, you can look at single particle spectral functions and also the response functions. So if the response functions are continuum, which typically would be in these interacting cases, then you would conclude that there are definitely at least fractionalization of quasi-particles, because if there was a sharp peak, there would be some electronic quasi-particle. Okay, then you can ask the question, suppose you start with certain degree of freedom, let's say some fractional degree of freedom, do you find a well-defined peak in your single particle response function? So if you don't, then you are sure that there is no quasi-particle, because if there is a branch cut in your, let's say in a technical language, if your Green's function has a branch cut, then you can clearly say that there are no quasi-particles. Another way to also look at it is you can follow Landau's prescription of expanding your energy eigenvalues in terms of quasi-particles. So if your system really has quasi-particles, what does it mean? Is that your low energy states are additive in the sense that your total energy you can write them as a linear combination of, let's say, single particle, quasi-particle energy, 2-particle energy, 3-particle, and so on. It's an additive quantity. So as a theoretical proof, if you are able to show that you cannot write it as an additive function with this proper form factors that Landau introduced, then you know that there are simply no quasi-particles, independent of what basis you are using, because simply you don't have this expansion anymore. So that's a more formal way to like really say that there are absolutely no quasi-particles.
So if I may ask, is it possible that you have a system and whether there are quasi-particles or not depends on the observable that you're looking at?
No. So there is really, you can show whether there is quasi-particle or no quasi-particle. That's it. I mean,
but it could be that, like, let's say if you're looking at one kind of, let's say some kind of a charge transport, maybe the charge is transported by only quasi-particles, but the energy transport is dominated by some other things which are not quasi-particle like.
So that's a good question. That's true. So certain observations that you may do may let's say may make you conclude from experiments that there are well-defined quasi-particles. And actually I will give you an example in a particular case that I'm going to show you, that you may conclude that there are quasi-particles, but if you look at other properties like transport and other stuff, then it's absolutely clear that there are no quasi-particles. But yeah, I agree with you. Like if you just take a single experiment, there might be a case that you may wrongly conclude that there are quasi-particles. So just to give you like let's say flash forward some slides in the model that I'm going to talk about, what will happen is that if you look at the electron Green's function, for instance, it will look like a Fermi liquid. But if you look at the spin correlation functions, it would not look like a Fermi liquid. So suppose if you do an experiment which only probes your single electron Green's function, like a photoemission experiment, let's say, then you may conclude that, oh, there is no criticality, there is no quasi-particle at all. But that won't be a complete conclusion, because if you look at transport, then the transport will clearly tell you that there are simply no electronic quasi-particles, because you wouldn't get a Fermi liquid-like behavior in transport. So what happens is that the single particle Green's function may sometimes be like the electron Green's function may sometimes be Fermi liquid-like, but the whole story can be much more complicated. Yeah, that's right. But still the conclusion is that there are no quasi-particles if you take the whole picture as a complete picture.
Okay.
So maybe, sorry.
Yeah.
So if I understand that last example, that may be perhaps in a case where it might there seem like single particle states, but what you said earlier about the additivity with 2-particle states and so on will not hold.
Exactly.
So,
yes.
so that's why the single particle Green's function might show up resonance or something like that, but the 2 particles and so on will not.
Yeah.
Okay. Thanks. So can you make this connection a bit more precise? That what do you mean by highly entangled phases of matter in the absence of quasi-particles?
So highly entangled phases is a more general statement. They could be like fractionalized excitations or no quasi-particles. There are different categories. So of course, as the name suggests, this means that there is really high entanglement and there is long-range entanglement in some sense. But I would hesitate to like really precisely give you a definition of highly entangled phases in terms of, let's say, entanglement entropy, because for instance, even if you consider the most simple case of non-Fermi liquid that you may know of, there are simply no good results or good understanding of how entanglement entropy behaves in this in such systems. So it's known that of course there are some log corrections to area law, but are they really? Can you make this more precise, or how they distinguish from, let's say, some trivial systems? It's not absolutely clear. So these are really open problems in this field. But yeah. So for quantum spin liquids, for instance, there are some results that are pretty known. or some topologically ordered phases, there are some exact results that are known, that you have area law entanglement plus some topological term. So there things are well defined, but in particular for non-Fermi liquids, things are not at all clear in terms of entanglement entropy. But it's clear that since you don't have quasi-particles, you simply don't have like Slater determinant or like a product state expansion for your ground state. So in that sense, it's like highly entangled.
But to define entanglement, I mean, presumably you have some bipartition in mind, or it's even at a more abstract?
Even at the basic level, like simple bipartitioning that you would do to calculate, let's say, von Neumann type of entanglement.
But could you then have a situation where you have quasi-particles? They are not just weakly dressed versions of your spatially local particles that you started with?
Sorry, what?
Suppose you have quasi-particles, but they are not simply some dressed versions of local sort of original degrees of freedom that you have, such that you had some more entanglement.
Yeah, that could happen. So I think in one-dimensional, these things can happen,
right,
where you have density
yes,
fluctuations as your quasi-particles. Yes.
Yes. Okay.
Yeah. Okay. So yeah, I was talking about highly entangled phases, and these are the two types. And so why do we care about these entangled phases? So one of the reasons is these anyons, so that I briefly mentioned in the context of quantum spin liquids. And these anyons are extremely important for robust topological quantum computation. So it has been shown that you can perform gate operations using anyons that are protected to decoherence and destruction. The second point, the second type of category that I mentioned, where you don't have quasi-particles, one of the prominent examples is the strange metal phase. And this is an extremely important phase in the understanding of the high TC cuprate systems or high TC superconductivity. Because ultimately, what you want to understand is how superconductivity emerges, and all these phase diagrams show that there is a strange metal phase just above the superconducting dome. So in some sense, the understanding of this phase is like one of the cornerstones of understanding this puzzle. And of course, even as a theorist, even if you don't care about experiments, even as a theorist, these entangled phases have enriched our understanding. So there have been extremely wonderful and beautiful mathematical development by connecting several theoretical techniques that have been developed in the context of, let's say, fractional quantum Hall effect and quantum spin liquids. So for instance, there have been some dualities that connect, let's say, nu equals 1/2 fractional quantum Hall effect to certain quantum spin liquids. So even at a very mathematical level, the understanding and the encountering these highly entangled phases have really enriched our understanding, theoretical understanding of this condensed matter physics. But there are, of course, lots of challenges. One of the main challenges is, as I mentioned, there are no sharp experimental features, so there are only continuum responses. So how do you really make out what really are you detecting? So for instance, one of the open challenges is like a smoking gun signature for quantum spin liquids, because you have fractionalized excitations, you detect some signal in your structure factor or some transport phenomena. How do you really conclude that it's really a quantum spin liquid? So this is one of the open challenges, both experimentally and theoretically, because experimentally they want to make cleaner and cleaner samples and very precise measurements. Theoretically, we want to really give them some very precise measurement and say that if you detect this, then really you have a quantum spin liquid. And also on a theoretical front, progress is very difficult, especially when you don't have quasi-particles, right? I mean, suppose when you have some quasi-particles, we usually have our many-body theory, and we can do our regular perturbation theory and make some progress. But I mean, if you don't have quasi-particles, then it's really difficult. I mean, you have to deal with all complicated businesses of branch cuts and so on. So that's why this field has been like really exciting for last few years, and many people have been interested in making developments. And this is one of the open arena in condensed matter physics in a comprehensive understanding of these highly entangled phases of matter. So of course, here I'm not going to give you a comprehensive theory or any comprehensive picture of these entangled phases, but I'm really going to focus on one particular problem. And that would be in the context of this strange metal and high TC cuprate materials. And as an example, and as a model system from which this work was motivated, I will consider high TC cuprates. So these are two-dimensional systems whose parent compound is basically an antiferromagnet. So this is a square lattice. Every arrow here is a spin where the electron charge degree of freedom has been gapped out. This is a Mott insulator in the sense that you cannot doubly occupy any state. So you have exactly one particle on every side. It's really an insulator, so it cannot really transport any charge. And this is what corresponds to doping equals 0. So you haven't done anything to the system. It's exactly one particle per side. So what typically happens in cuprate system to induce superconductivity is that you hole dope or electron dope the system. So in this particular case, I'm showing hole doping, meaning you remove some electrons from your system. So what happens is that your system your electrons can now hop around because now there is an empty space, so there is no problem of double occupancy. This electron can hop here and so on. So there is some conduction now, and you have some metallic phases. So this is what is the general picture of hole doped cuprates from the material side. You have some parent antiferromagnet, and you start hole doping. And it has a very complicated phase diagram and pretty complex. So let me just walk you through. So here the y-axis is the temperature, x-axis is the hole doping. So this point is, so this axis is basically 0 hole doping, the parent Mott insulating compound, and it's an antiferromagnet. You start hole doping it slightly, there's still some antiferromagnetic order. Then you have some very complicated phases here, some competing orders with lots of different types of magnetic ordering, charge ordering, and spin density waves and everything. You have some pseudo-gap phase, basically it's some metallic phase. Then you dope further, you get a superconductivity, which is one of the interesting phases. And then you have a Fermi liquid phase at high doping. And this is what is the non-Fermi liquid phase emerging above this superconducting dome, which is the strange metal. So just to briefly recapitulate some of the discussion that we had in the beginning and also in the context of the questions that were raised. So this is the strange metal, which is the non-Fermi liquid phase at low temperatures, and it has the property that the resistivity is linear in temperature instead of quadratic, like a Fermi liquid. And also at high temperature, there is also a phase where also you have a linear in temperature resistivity, but that's a bad metal. So there the physics is slightly different. It's not connected to the physics of this strange metal. So the spectacular thing about this strange metal is that this T linear resistivity survives all the way to very small temperature in the limit T going to 0. So that's what a strange metal is. And what we are going to talk about is in the vicinity of these pieces. So this, as you can see, even in the most schematic fashion that I can draw, it still looks very intimidating and a very complex phase diagram. So how do we really go about talking about and solving about this problem? So like mathematically, you can ask the question, really, what's really the question? Because I mean, a mathematician has a theorem to prove and a well-defined question, and you can ask, can you show certain things, and can you prove certain things, and there's a well-defined question. So what do you really mean by understanding this cuprate phase diagram or high TC superconductivity? So in the recent years, there have been really interesting experiments that I believe have kind of sharpened the question, and you can ask certain very fundamental questions amid this complexity and very intricate phase diagram. So let me walk you through some very recent experimental observations that motivated this work. So for instance, in the left plot here, this is the specific heat as a function of hole doping. So again, the y-axis is the same, just like the previous phase diagram. What you see is, forget about lots of details. This has been done on several compounds, but the main thing to note here is that there is certain critical value of doping P star or PC, where you have signatures of some singularity, like the heat capacity is diverging, indicating that there is something strange happening or some phase transition happening at some critical value of doping. The right plot is basically electrical Hall measurement. So this is Hall number as a function of hole doping. Again, this has been done for different compounds, but what the main thing to note here is that at low doping, if you fit the data points, it fits to a number where the charge carrier density is P, proportional to your hole doping. And suddenly, after a certain value of doping, it jumps to 1 plus P. So again, these experiments indicate that there is something drastic happening at some critical value of doping. And there are further experiments from R-pairs photoemission, which also suggest that there is some critical value of doping where very drastic things are happening.
Sorry, just a clarification. So this is, you apply a magnetic field and kill the superconductivity here? In the specific heat?
No, not this one.
Not this one.
No.
So C by T means you're, okay, because it's a D wave, it has also linear T specific heat, is it?
Yeah.
I see. And then, and the point is that at some particular value, this is diverging in some way.
Yeah.
And do we know how it diverges?
You mean the exponent or the power law? I don't think is like precisely known, but it's believed, at least from various theories, we believe it should be like T log T.
So there's like a Van Hove kind of
divergence. Yeah.
There's like a Van Hove singularity of some kind?
A map?
Van Hove singularity.
No, I don't think there's a Van Hove singularity.
That's not what it is.
No.
Sorry. So this whole doping, this transition seems to happen somewhere 0.2, 0.24 or something. Does that where does that correspond to in that
in the phase diagram? Yeah, so that's roughly here. So that's roughly somewhere here.
Right in the middle of this.
I'll come to like precisely again to this point. Yeah, so that's roughly inside the superconducting dome, somewhere halfway between. So in the condensed matter or cuprate community, this particular doping where strange things happen is called optimal doping, and usually that's also the point where the TC of this superconducting dome is maximum.
But I mean, just as an outsider, I used to hear that the superconducting phase of the high TC superconductors is very similar to that of ordinary superconductors. It's only this. But you're saying this sort of phenomenon only happens for high TC superconductors.
Yeah. So there are two things. Of course, the superconductivity, if you like ask the question, what's the big deal about the superconductivity? I think there are several like theories and explanation and very well understood properties of superconductivity, like how the Fermi surface is and what's the property of the superconductor. That is well understood. What is not understood is like why this superconductivity happens here, and in particular, how does this strange metal phase emerges out of this superconductor?
Right.
And then the question is that maybe, so that would be my main point, that the superconductor, the strange metal actually arises from certain critical point which is hidden inside the superconducting dome. And so that would, like the understanding of this strange metal is kind of fundamental in the sense that once you understand that, then maybe you can like understand everything emerging.
Okay, so you're saying that this might be a reflection of the T goes to 0 critical point on that doping line.
Exactly.
That's. The second graph is on the same system or a different system?
Some of them are same. So for example, this LSCO is the same one, YBCO is same. Here in this plot, there are some other compounds as well measured. So here, these two are the same here, LSCO and YBCO.
I can't make out, but it seems as if the transition here is happening a little to the left of the transition.
Yeah, so there is of course some margin of error, and also you see that it's not like absolutely sharp jump. It's not a step function, but it's like a slowly gradual thing. And yeah, these are details of the experiments.
Right, but is it believed that they are kind of correlated, or they are kind of reflections of the same thing up to experimental error? Okay.
That's the general consensus, yes.
Thanks.
Sorry, this right plot, that's done in magnetic field, right? Otherwise...
Yes, that's true. It's a Hall measurement, yeah.
Okay. And the left, it is in 0 magnetic field?
Yeah.
Actually, what's the temperature at which these experiments are done?
So it's in the limit of T going to 0. So I don't recall like exactly what's the temperature, but it's quite small. Maybe I might be recalling incorrectly. There might be some small field as well in this particular case too.
So if I'm going to go into a superconductor, then why would that reveal anything about the quantum critical point? Because I'm very.
I think even in this case, you have to kill the superconductivity by applying
that's what.
Field. Yeah, sorry. So these are basically the two experiments indicating that there are certain drastic things happening around some PC. Then there's also evidence from magnetic measurements where people have measured, again, killing the superconductivity. that you have some spin glass magnetic order at low doping, and the spin glass magnetic order essentially vanishes around the same value of doping that the other two experiments are suggesting. So this, like collectively, this set of experiments, and sorry, before I go to the main point, there are also a set of experiments which are done exactly in the strange metal phase. So there are not so many because these experiments in this strange metal are extremely difficult. But one of them is this density fluctuations, which is measured in electron energy loss spectroscopy. So there are several plots. The main thing to note here is this plot, which corresponds to the optimal doping, meaning where the superconducting temperature is highest, and then you just go above it and you are in the strange metal phase. So here, what you measure is on the y-axis is the response function, which is density-density correlation as a function of energy. And you see the main conclusion of this work is that there is a frequency-independent feature of this density-density correlation, which is one of the things that I mentioned in the beginning, that there are these broad responses in this strange metal or non-Fermi liquids. And here it's even extreme because it's really flat. It's independent of frequency. So this is what sometimes we call as a marginal behavior in some sense. And these three plots are basically just below and above doping of this optimal doping in the strange metal. So collectively, these experiments, what they suggest in the context of this phase diagram is that is there a quantum critical point underneath this superconducting dome? So precisely what you were asking. So essentially, the question now boils down to saying, can you have a theoretical model, or can you describe a phase transition between a low doping phase, which has a carrier density P, and a high doping phase, which is a Fermi liquid-like with carrier density 1 plus P, separated by a quantum critical point, such that this quantum critical point can lead to a strange metal behavior. So you don't want just any quantum critical point. You want a quantum critical point with the property that the phase that would emerge from this quantum critical point should give you this strange metal kind of behavior, meaning T linear resistivity and so on. So that's the question that I'm going to address today, and I will describe a simple theoretical model. It's a toy model, of course, it's not a very realistic model, but nevertheless, I will show that you can capture all the key aspects of this cuprate phenomenology, ignoring all the distractions of many complicated phases that are arising around this main phenomenon. So this is the fundamental question that I will try to address as in a toy model. And the model that I will be considering is a random TJ model, which is basically doping Mott insulator, but with some randomness inbuilt in it. So before I get to really the model itself, you may, of course, criticize and ask, like, why do you want to consider a random model? So let me just briefly motivate why we are interested and why we are considering such a random model. So one very naive justification is that there is disorder and randomness in any real material. I mean, essentially, even if you consider very clean cuprate, what you are doing is you're removing electrons from it. So in a way, you are kind of making it disordered. So there has to be some like changes in your exchange interactions, hopping, and so on. So there is some randomness or disorder in real systems. The critical phases and points that we are interested in particular the one that I just showed you, does happen, is not really affected by disorder. So even if you, like, as I mentioned, you are like hole doping or electron doping, you are changing electron constants, you take different materials which has different chemistry, but still you fundamentally see the same physics. So in some sense, the underlying physics is really not so much dependent on randomness or disorder, and it does happen even in presence of that. And of course, as a theorist, our life is simpler when you consider these random models that I'm going to show you. And there's also a connection to certain lattice models. Connection in the sense not really an exact map, but there is some connection to lattice models if you consider them within a dynamical mean field theory. So if you're not aware of dynamical mean field theory, in 2 sentences, what it means is that you're aware of your usual mean field theory, the textbook one where you simply average out the fluctuations from your neighboring spins. Let's say when you do some Ising ferromagnet or something, there you essentially ignore all fluctuations. So all, I mean, spatial and temporal, everything. In dynamical mean field theory, what you do is you average out and ignore all the spatial fluctuations, but you keep temporal fluctuations, and that's why the name dynamical mean field theory. So mathematically, it has been shown that in infinite dimensions, this is an exact approximation. So what this means, like the statement that you keep temporal fluctuations but ignore spatial fluctuations, it translates into saying that if you consider your self-energy, for instance, many-body self-energy, in general, it can have both momentum and frequency dependence. In the naive mean field theory, you simply put it to a constant, throw away k and omega dependence both. In dynamical mean field theory, you throw away k dependence, but you have omega dependence. And this is justified, and it has been shown it's exact in infinite dimensions. In finite dimension, of course, it's an approximation, and that's why it's called dynamical mean field theory. So what you can show is that if you, let's say, take a square lattice and do a dynamical mean field theory and calculate the saddle point equations of this theory, then they are exactly same as that you would get from these random models that I'm going to talk about on all-to-all connectivity in a fully connected lattice. So that's the connection. So there is no exact map, but there is a connection between the two. So that's why I'm interested in this random, and it's exciting to consider this. And also one more point that I usually try to make, but I'm not bold enough to always say this aloud, is that of course we tend to work with Hubbard model, and we are obsessed with that you have some local interaction, but ultimately these are electronic systems. I mean, ultimately you have a Coulomb interaction in reality, and the Coulomb interaction is of course a long range interactions. So in some sense, it's not completely absurd to kind of consider models as a toy model, consider systems where you have kind of all-to-all interactions. Of course, it's an extreme case, but still there is some logic behind or some justification to consider all-to-all interactions. So let me start with the Mott insulating case as a random model and all-to-all model. So this is the Sachdev-Ye model, which was considered back in 1993. So this is simply a Heisenberg model that we learn in our classroom. And now the difference is that the exchange interaction Jij between two spins on site I and j are not constant, but independent random numbers such that their mean is 0 and their mean square value is j square. So as you can see, the interaction is all to all. It's not nearest neighbor like we are used to. Really, every spin is coupled to every other spin. So it's a fully connected lattice. So this was solved by introducing such a parton construction where you now break down your spin write down your spin in terms of some fermionic spin-ons, and you enlarge your symmetry from SU2 to SUM. And it was shown that you can systematically calculate the saddle point equations in this large M limit. And the main result was that the Green's function has this 1 over square root tau, where tau is your imaginary time. And the most spectacular result is that the spin-spin correlator decays as 1 over tau. So it decays really fast. So just to put it more physically, if you Fourier transform this in real frequency, it translates into a constant. So it's independent of frequency. So this is really remarkable, right? I mean, all the response functions, for instance, for like ordinary magnets or some systems that we are used to, they have certain like frequency dependence. So this is really frequency independent. That's why it was called like a marginal behavior. And it was very interesting result in that sense. Now, of course, this SY model has given rise to like flurry of works in the context of Sachdev-Ye-Kitaev model, where instead of now spin-spin interaction, you consider a 4 fermion interaction with random and all-to-all again. And this has like made tremendous progress in several fields, including condensed matter and high energy physics. And also it has some connections to gravitation and also to many body chaos and so on. I'm not an expert on all these other aspects of SYK model, and I won't be talking about them in this context because they are not relevant. But I'm just highlighting that this work has like given rise to a completely new, different field. So now what we are going to do is that we have this Mott insulator and ask the question, let's dope it, just like what people do in cuprates. So let's consider the TJ model. So now what I have done is removed some electrons from the system, and now we have holes, basically. Now, the main thing is that since we started from the Mott insulator, of course, we don't have any double occupancy. So you cannot occupy 2 electrons on the same site. So that's one of the constraints. And now, apart from these Heisenberg interactions between the spins, you also have hopping of the electrons. So because there are holes, the electrons can hop, and there is some chemical potential. So just to reiterate, there are 3 states on every site that you can have, either empty or one of the 2 singly occupied states. So the electrons can hop in this fashion. And now to make progress, what we do is consider this SU12 algebra, where we fractionalize our electron in 2 degrees of freedom. One is a holon and one is a spin-on.
Just a couple of just clarification. So what? So Tij are random?
Yes. Oh, sorry. So I should mention this. So both Tij and Jij are random and independent variables.
And no. How is Tij distributed?
So it's the same. Like average Tij is 0, and the mean square value is T square. So just similar to the J square, J term.
I see. So, but you don't believe that the square lattice structure is important at all?
No. In fact, there is no lattice.
There's no lattice.
It's all to all connected. So there is no lattice. It's really like a 0-dimensional problem. So now we have the basic degrees of freedom. So we have 3 states, as I said. So there is an empty state, which is a holon. And then there are the singly occupied states, which are spin-ons. So they carry the spin degree of freedom. So now you can partition or fractionalize your electron in terms of a spin-on and a holon. And similarly, you can write the electron operator in terms of the spin-ons. And of course, this comes with this constraint that F dagger F plus B dagger B has to be 1, because your Hilbert space is ultimately, again, just 3 particles. You cannot occupy like many bosons or anything in this case.
So it's the doped version of the SY-1.
Right, exactly, yeah. And of course, there is an alternative and completely equivalent description where you make the spin-ons to be bosonic and the holons to be fermionic. And this is called as SU2 superalgebra. So they are completely equivalent, and you can use any picture. So in this particular case, we will be using this representation with SU12 superalgebra.
Darshan, so would you discuss why this Coulomb phase would be stable to gauge fluctuations in presence of that quadratic term at some point?
So which quadratic term?
The Tij term, right? So normally in SYK model, if you have a quadratic term, all the SYK physics is lost at low enough energy scales. Here so here it gives rise to some hopping, okay? And presumably that's like, if I had only that state, it's some Anderson localized state, okay? And that does not have holons or spin-ons, okay? So would you justify how that state is suppressed?
Yeah.
Okay.
So that's a good question, actually. So like people who are aware with SYK literature, what happens is usually in SYK, you have 4 fermion interaction, and it's a known result that as soon as you have like a single particle perturbation to it, meaning something like this, C dagger C, then it completely like destroys the SYK physics. Then you get some like usual Fermi liquid or some localization or something. Amazing thing is that here it doesn't destroy the SYK physics. And the reason is that you can see it from this fractionalization. So now you represent your spin operator in terms of fermions or spin-ons. It's a 4 fermion operator. If you represent your electron operator now, C dagger C, it's also a 4 particle operator again. So it's really like SYK.
That's in the Coulomb phase when this fractionalization is the right thing to do, right? But how do I see that this fractionalization survives? Why doesn't it confine?
So this I will show you in terms of some renormalization group argument, that this is really a stable phase, and like the stable point in this argument. Yeah. So it's not destroyed, but at least like naively you can see that these two are kind of on the equal footing. So as long as you are in a situation where the energies of the energies of the 3 levels are same, you got to have this physics being survived. Of course, you're right that what happens away from this point, we of course don't know. So my argument would be concentrated near this critical point where this remark is true, that these 3 states are almost degenerate, and these 2 energy scales, these 2 terms are on an equal footing, and the SYK physics survives. But of course, away from this, even in the renormalization group sense that I'm going to discuss, I absolutely don't know what is going to happen at very large fluctuations away from this point. But then I will show you some recent work that we have been doing, and that's what I will talk tomorrow, that we have some understanding of even the phases away from this critical point, and that's something I will discuss for this particular model in a large M context.
So just to understand, at this critical point, the monopole is irrelevant of that gauge field?
Yeah, yes.
Okay.
So even strictly speaking, there's not even any emergent gauge field at this level in this SYK-type model. So there are really no emergent gauge fields or gauge fluctuations in this sense.
But the first C as F into B, there is a gauge field,
yeah, so
right?
there is an emergent U1 gauge symmetry, yes, but there are no gauge fluctuations at this level that are relevant.
Okay.
Maybe we can discuss this in detail later, but yeah, at this point, these are not important. But you are right. I mean, in principle, there could be.
So what happens if you tune mu to be at half filling, so that?
Yeah, so if you are exactly at half filling, then you are back to SY. So
it'll be just go back to SY.
Yes,
I see.
Yes.
I see. I see. Okay, I'll ask the question later.
Sure. So now the way to proceed is that you simply use this parton or SU12 algebra and write down the action of your corresponding to this Hamiltonian, and then you basically do the usual business. Because you have these random variables, you average over the disorder. So you perform a disorder average, and then you take the limit where your number of sites goes to infinity. So that's called the large volume limit. So you want to work in the thermodynamic limit, and this effectively gives you a single site action. So your problem now reduces to a single site problem. So this is also what typically happens in, let's say, dynamical mean field theory, where you average out your fluctuations and then effectively you arrive at a single site problem. So this is the partition function. So this is the bare term, the Berry phase term, where you just have the dynamics of F dagger F, B dagger B. This lambda is introduced as a Lagrange multiplier corresponding to the constraint that I mentioned, that F dagger F plus B dagger B has to be 1. And these are the spin. Sorry, this is the electron hopping. So this is C dagger C, F dagger B, B dagger F, and this is S dot S term basically. And there is also some chemical potential corresponding to your partons, which is you can tune. And in particular, the theory that I would be interested in, so where the critical point arises, corresponds to S0 to be 0. So you tune your system to the critical point and then ask the question, what's happening around and whether you find some stable critical point. But the main point in this analysis is that you do a bunch of Hubbard-Stratonovich transformations in arriving at this single site action. And the consequence of these Hubbard-Stratonovich transformations is that there are a couple of self-consistency conditions that you have to satisfy. So it's not enough to just solve this problem for any arbitrary R and Q fields, which are functions of these imaginary times. You also have to impose this self-consistency condition that the field R here has to be the time correlator of your electron operator, and the field Q here has to be the spin correlator in this imaginary time. So that's actually a very tricky part, and that's what makes solving this problem hard, because you have to impose these self-consistency conditions. So what we do to make progress is let's ignore these self-consistency conditions for the moment. We will come back to them and we will impose and show that everything is consistent. But for the moment, let's ignore those self-consistency conditions and assume there is some power law behavior for this R and Q fields. So let's assume Q decays with respect to imaginary time with an exponent d minus 1, and the field R decays with time with an exponent R plus 1. And these R and D are like some arbitrary numbers. I have not fixed or given any physical meaning to this. So these are just some numbers. And just for some historical reasons, it's written in this fashion, d minus 1 and R plus 1, because these are connected to some of the works that people have done in the context of Kondo impurity problems where such notations were introduced. But these are just some numbers in this particular problem, nothing to do with anything. And now what you do is, important thing is that you have these quartic terms in your action, right? You have this F dagger B, B dagger F, and this S dot S is again F dagger F, F dagger F, and you want to decouple this. So So one way to decouple these quartic terms is by introducing some baths. So we introduce some fermionic and bosonic baths. So let me walk you through what exactly is happening. So these are, of course, the quadratic terms or hoppings of f dagger f, b dagger b, which is trivial. Now what you do is you decouple this field. So you wrote down R as some power law decay. And now you decouple f dagger b, b dagger f, which is essentially c dagger c, by introducing a fermionic bath psi. So now this fermionic bath psi has the property that its correlator is exactly like Q. So if you integrate out psi, you essentially get back your original Hamiltonian with f dagger b, b dagger f. And similarly, you do for the other terms. So you introduce this bosonic bath phi, such that once you integrate with the proper correlator corresponding to this, such that once you integrate phi, you again get back the s dot s kind of term. So essentially this g naught and gamma naught are nothing but related to up to some prefactors related to your t square and j square that you started. And these are, of course, the bath free bath Hamiltonian terms. So this is for the fermions, this is for the bosons. So essentially what we have done is we took our original SY model with doping, we introduced this fractionalization, we did the disorder average, we had a single site problem with certain self-consistency conditions. And to make progress, we mapped this problem to an impurity problem. I mean, the reason is that we know how to solve impurity problems from quantum physics literature, and that's the reason why we do this. So in some sense, this is like a super spin coupled to baths. It's really like a super Kondo problem. It's a slightly higher version of a Kondo problem. Yep.
What I mean, there's the momentum there. The label PSY-K. The K is the kind
for
of
the bath. Yeah.
Yeah, but I mean that's when you do the Fourier transform with respect to the tau, right?
No, so this is completely independent of your original partons or anything. So this K or the momentum of the fermionic bath doesn't impact or doesn't influence anything on your F or B or C or S operators. This is completely independent. So you have just introduced some arbitrary bath in your
right. But I mean, you're getting that functional form mod K to the R as a kind of Fourier transform of your original.
Yeah, because we want it to be in this form.
Yeah,
exactly.
So that when you integrate out,
so that's the reason why this particular
you get that
choice of density.
So in that sense, the K arises from the Fourier transform. I mean, that's the origin of the.
Yeah, or you can say that I make a choice such that I get this correct Fourier transform.
Correct, this thing. Okay, but then the boson term, you have a ddx. So
this is written in real space, but if you Fourier transform, you can also write it like d to the power, k to the power some d minus 2 or something.
Right, so you're thinking of that as some some actual space, or you're just writing it
just as it's a representation. Yeah. So actually, this is again also written for historical reasons in different notations. I mean, I could have also written the fermionic bath Hamiltonian exactly in this form with some proper prefactors, and also I could have written the bosons in terms of this. That actually we did in one of the later works when we consider like the possibility of supersymmetry in this model, which I'm not going to talk about here. But yeah, in this particular problem in this particular time, by solving this for the first time, just for historical reasons, we just use these notations that people had already used.
Can I ask a question?
Yeah.
So can you go one slide early?
Yep.
Yeah, this slide. Now, what is in the standard SYK model that we are familiar with, you can see the emergence of the reparameterization symmetry actually by simply setting the d by d tau terms to 0. That's long wavelength.
Right.
I don't see anything like that here in some, I'm not able to just see it.
Yeah.
That there is an infrared fixed point.
Yeah, so here it's not extremely easy to see unless you tune your system to the critical point. You go to the critical point where you set S0 to 0. And then there's also a complication because you have this constraint. So in the SYK case, there is no constraint that comes about even when you do, when you do this G sigma action and so on. Here, because you introduce these partons, there is also this constraint, and that's why you have this Lagrange multiplier lambda. So so the way to see this time reparameterization symmetry is once it becomes more clear if you work in the large M limit. So here, I'm not working in the large M limit, I'm working in really with SU2 spins. So really to see this time reparameterization symmetry, what you can do is, and this is also what we have done, is that instead of working the way I'm showing it to you now, there's also a complementary way where you can enlarge your symmetry from SU2 to SUM and also introduce another index for the holons and so on. And then once you write the saddle point equations in that language, you can immediately see the time reparameterization symmetry, because then there things are slightly more easier and you don't have these complications of lambda. I mean it's still there, but at the saddle point level you can immediately see there. So here I'm not showing you any saddle point equations or anything. So
I understand, but then how do you know there is an infrared fixed point? It's just a guess?
No, I will show you by doing renormalization group theory.
Okay. All right. Thank you.
Okay, yeah, I just had a basic question. So, I mean, you're trying to understand this phase transition in the doped superconductor,
right.
And this model you have written. So, is the doping in that in the chemical potential? Is that where you put the doping?
Yeah, that basically tunes. So the mu is selected such that it gives you the correct
doping. Okay, so you basically now want to in this model you want to change mu and see if you get the transition. And so now after all this, where is mu now gone?
Yeah, so it's proportional to this S naught. So roughly mu is selected such that S naught equals 0 takes you to this PC value of PC. So that's the convention. So it's slightly non-transparent in this.
Okay, right now it's not clear. This has a transition, right? That's what you'll show.
Yeah,
okay.
Yeah. But roughly speaking, this mu is hidden in this S0, and this the choice is made such that if you set S0 to 0, then your mu is the one corresponding to the critical value of doping. So the conventions are set like that.
Okay.
Yeah, but I agree. It's not like transparent immediately from here what mu is, but it's hidden here in this S0.
Thanks.
Right, so we now have to solve this impurity problem, essentially, this supercondo problem. What you can do is look at the scaling dimensions of different operators and coupling constants, G, gamma, and the other operators. And what you see is that there are actually two small parameters in your theory, namely epsilon, which is 3 minus D, and R bar, which is 1 minus R over 2. And these, in terms of these two small parameters, you can now perform a renormalization group theory. And this is what we did. And this is what the renormalization group flow looks like. So just to, if you're unfamiliar with this like Kondo kind of problem or doing renormalization group theory, it's basically
sorry.
Yeah, no worries.
Small technical question. So the psi alpha 0 will be sum over k of psi k, right? The psi alpha 0.
Yes, that's right. Yes, that's right. Yeah. So psi 0 is really like the local function because we want to couple the bath to the impurity, which is on a single side. Yeah, but thanks for pointing that out. Yes, it's really local. Similarly, this phi 0 is local. It's really on a single point that you want to couple it. And now we do the renormalization group in terms of these two small parameters. So there we get a set of fixed points and the renormalization group flow in this parameter space G and gamma. So the x-axis is G, y-axis is gamma, and what you see, there are 4 fixed points. So the blue one is the trivial fixed point, 0, 0. The green one is a fixed point where G is 0, but gamma is non-zero. This fixed point is the one where gamma is 0, but G is non-zero. So if you recapitulate, G is the one that is proportional to T square, or the hopping piece. Gamma is the one proportional to the exchange interaction. So when gamma is not 0, but G is 0, this is like the original SY fixed point. And you see that it's stable as long as like G is 0. So if you would have considered just the SY model, you would get this fixed point, and it has all those properties of the SY model that were discussed and the solutions that were found. This particular fixed point is actually related to another impurity problem, which is studied in the context of Kondo models. It's called the asymmetric Anderson model. So it has the properties of that. And again, if gamma is 0, this is the only stable fixed point here. But now we have both gamma and G to be non-zero, and we find a new non-trivial fixed point with this, with the property that it's stable in your parameter space G and gamma. And this is the critical point. This is the stable critical point that I will show you corresponds to the critical doping that I was talking about in the beginning. So we show that this is stable. And now we can ask what does it really mean, and what are the physical properties corresponding to this stable fixed point. So as I said, okay, so before I go to there, let's look at the spin and the electron critical exponents. So of course, your electron correlator would have some power law with some exponent eta c, the scaling dimension or the anomalous dimension. Yeah.
Just to get a bigger picture. So you made an ansatz for this R tau and Q tau, which is 1 by, and then you are saying that there is a consistent solution for R. That's what you have demonstrated, right?
Yeah, yeah. Okay. So I will get to that. So I haven't yet fully shown you that this is really consistent. I'm getting there, yes, but good point.
Sorry, the previous RG, the beta function equations. So you're doing a like an epsilon expansion, and in terms of that R bar, and the fixed points are all of order
epsilon and R bar
to vary. So that's your control parameter, and you kept terms only to the same order in.
Yes. So here, of course, yeah, we did it at 1 loop, it's already stable, but we also checked that even at 2 loop, this is true.
So these are given to 2 loop.
Yes, that's right. Yeah.
Thanks.
Just to show that we did it to 2 loop. Okay, so basically then let's look at the electron and the spin correlators, because these are the physical observables. The partons that we talked about, they are not physical observables. These are the physical observables. And what does like a correlator in this form mean really in a physical observable? Ultimately, in some spectroscopic or scattering experiment, what you measure is the imaginary part of the spin-spin correlator or imaginary part of your Green's function on the real frequency. And this is denoted by chi double prime of C or chi double prime of S, meaning the imaginary part. And they scale as omega power eta minus 1 in this fashion. Okay, so now what we do is the important result of this RG analysis is that although we can do this perturbative RG only to certain loop, like 2 loop order in this case, we can actually prove to all orders that eta C is exactly 2R bar and eta S is exactly epsilon. So this is really an exact result, and this you can just show by looking at the beta functions and the scaling dimensions and so on. And if you're interested, I would be happy to talk about it later after the talk, like how really to prove that this is an exact statement. So this is like a very nice result, because although we cannot do the perturbation theory to all orders, we actually have an exact statement about the exponent. So, but it's actually also important that you get a fixed point. So if the fixed point is not stable, then of course this is completely meaningless. But fortunately, or like it turns out that the fixed point is also stable, and we also have an exact result for the corresponding exponents.
So this statement and also the fixed point, both are stable to gauge fluctuations?
Yes.
You would discuss that?
Not here, but
okay, maybe after the talk.
At this level, there are no gauge fluctuations.
Yeah, and this is mean field.
Yes, exactly. Okay. But I mean, we can talk about this in detail, but in one sentence, I can tell you is that it's at this level, I mean, within this theory, there are no gauge fluctuations because we are doing this sort of dynamical mean field theory. And there's also not absolutely clear-cut way of how you would improve on that and like take into account gauge fluctuations. So that's one of the open questions, but at least at this level, it seems to be under control. And I can talk about it slightly in more detail maybe later.
So this anomalous dimensions being uncorrected, this is probably the 1 loop result or something.
No, this is exact.
No, no, I meant, so you can get the, this by just solving
Sure,
at one
yeah,
loop, and
yeah.
then you can
Yeah.
then you argue that it's exact. But this is special only to these two correlators, or is there a larger class of correlators for which such a thing is?
Only these two correlators.
I see.
Yeah. So there is a very special property. So the exponents of this correlator turn out to be intimately related to the RG flow equations that you write and the beta functions. And that's why when you try to derive, let's say what these correlators would be, you can put the beta functions in such a form that you can immediately prove that, let's say if G is not 0, then the correlator for the electron has to be exactly 2R bar. And if gamma is not 0, then the exponent of the spin has to be epsilon. And because in this particular case, both are non-zero, so we know both to be exactly this. Yeah, but it's only special to the electron and the spin in this particular case. But there's, yeah, sorry. Maybe let me just finish one comment on this, just to comment, like, since you're interested in, like, if there are other correlators where you can have exact result. So in this problem, not, but for instance, if you consider on top of the model that I'm considering here, you can also extend this model by including some density fluctuations. And this is also an interesting extension of this TJ model that we consider. And there actually you can also show that even the density correlator has an exact result because it's somehow inbuilt in your RG equations, but not here.
In general, usually when some correlators are protected, I mean, you see this when there are some conserved currents or something like that, but there's no underlying symmetry or integrability or something like that, which is giving you
not here.
This.
Yeah, but that's actually an interesting point. I thought about it, but yeah, at least I don't like immediately see like a very deep reason why it always has to be like an exact result.
Yeah. So sorry, can we go back to the flow
Can I
diagram?
ask a question?
Yeah.
Sorry, am I interrupting somebody then?
No, go ahead, Sveta. Go ahead.
Okay, sorry. Yeah, so, your beta functions are not exact. I mean, they're just done perturbatively, right?
That's right.
Yet you claim that these exponents, for some reason, you haven't said perhaps, or I have no clue that these are exact. Why?
Yeah, so it's not immediately clear from this. I mean, I have to go through a bunch of things and relations that you can use to prove. But I would be happy to discuss that later, definitely. But yeah, I cannot immediately show you from like these expressions or from this form that I have on the slides why this is an exact statement. But yeah, I would be happy to derive it. Maybe I can also.
What's the principle? I mean, you don't have to give the details. I mean, like, Rajesh was saying, some conservation law, etc. I mean, what's it?
Yeah, so as I said, I do not really see like if there is really any conservation law as such, but essentially what happens is that you get a form like, let's say beta of G. Let me see if I can get this right.
Can they see the black hole? Yes, once you
Okay, can you see me writing now?
Yeah, I can see.
Let me just try and see if I get this correct from memory. So this beta G is roughly turns out to be like proportional, sorry, eta C. You can prove that it is exactly G times yeah, that's the thing. Let's see. No, we don't need this. Yeah, I think, yeah, you get this form essentially for the beta functions. And so what it means is that at the fixed points when beta, let's say beta G is 0, If G is not 0, then eta C has to be exactly R bar. And similarly, if beta gamma goes to 0, then if gamma is not 0, then eta S has to be exactly 2R bar. So this is the roughly the form that I get. But apart from this, I cannot really put any physical meaning or like symmetries or like arguments why this is really an exact result at this point. Yeah, sorry about that.
No. I mean, for example, in the usual SYK model, it just pops out, right? The exponents pop out from the energy, the fact that you are at an infrared fixed point. Is there something like that, that let's assume that you are at an infrared fixed point, everything is exact. Then you're saying, yeah, still okay, maybe we can discuss later.
Yeah, I would be happy to learn if there's something interesting. Yeah, but at this point, I cannot really pinpoint any symmetry or underlying physical argument to this.
Maybe there is conformal symmetry. That's what I'm trying.
I mean, of course, there is conformal symmetry, but
that will not fix it.
In this form, when you write these RG equations, it's not evident. I mean, it's
no,
not
no,
obvious that there is any conformal symmetry.
No,
yeah. So if you actually write down in this large M theory, there it's slightly more transparent because there you have saddle point equations and the solutions that you get, they are conformal. They have conformal symmetry. So there I agree. So there is an argument using that language, but if you stick to this RG argument perfectly for SU2, then I don't see any like immediately any symmetry or anything that immediately tells you that it has to be the case. But it just turns out that the beta function have this form. Yeah.
Thank you.
Yeah, so I'm again trying to understand this R and D dependence.
Yeah.
So can we go back to that?
Yeah, sure.
So this is the beta function throughout this phase or throughout the diagram, or is it near it's near the red fixed point?
No, it's in the entire.
Then how do I get the SY result for the spin-spin correlator, like 1 by tau?
I'll show you in a moment.
Okay.
Yeah. So right now what I've just done is solve this RG for this impurity model, and you get some beta function in terms of your small parameters epsilon and R bar, and you ask the question, are there fixed points and what's the flow? And then I'm just showing you that there are these 4 fixed points with the flow such that there is this non-trivial fixed point which is stable. And I'll show you like what this like stable fixed point really means. Or like what does it correspond to. And one of the things that you get is this exact result, that at this non-trivial fixed point, the exponents for the electron and the spin have this property.
So is there some statement about higher point functions of, let's say, C and S? Do you know what the scalings are there? You know, like.
Or you mean like if I make some composite operators, like even higher order composite operators? No, I don't know if they're like exact results.
But there's no reason to believe that those guys are exactly understandable.
So they are very. Let me see how to put this. Yeah, in general, to calculate these composite operators, you also need to like carefully work out the vertex corrections for this composite operator. And I cannot like immediately guess if for these higher orders they will be same. So it turns out, so that's the beauty actually, that so even for this S and C operators, these are actually composite operators in terms of your partons that you have been working, right? It just turns out that the vertex corrections that you get for these composite operators exactly cancels some of the terms that you get from, let's say, the wave function renormalization, and that's why you have this result. But again, I don't think like I cannot put it in terms of symmetry or some like protected integrability.
What about, let's say, 3-point function of C dagger and S?
C dagger and S.
So C dagger and S. You have some.
Yeah, I think it will be something similar to this eta S and eta C, and there would be an exact result, because essentially one way to actually to calculate this composite operator is also you can precisely choose this 3-leg correlator, and this is how you can also calculate. So I presume that for this correlator also you would have probably some combination of eta S and eta C, but yeah, I won't be able to tell you exactly what it is.
Okay.
It should be fixed by conformal interactions.
Yes.
So they are anomalous dimensions.
I see.
Definitely, I mean, up to some overall numerator.
What is a large N version of these statements?
Large M version.
Yeah.
There also you can you get similar results.
Just 1 over N corrections.
No, we haven't looked at 1 over M corrections, but we believe that because these are to some extent exact results, so even in the large M limit, the 1 over M corrections shouldn't destroy these. Yeah, but here it's more fundamental or like more exact because this is not even 1 over M like large M. This is SU2 directly. Yeah. So I haven't enlarged symmetry here. Like you remember, I mean, I'm working with really SU2. So in that sense, this is like even more interesting. So yeah, so here I didn't do any large M or symmetry enlargement. I directly worked with SU2. So there is no question of like 1 over M corrections or anything. This is like an exact result for SU2. Okay, so this is just the properties of this fixed point, but now we have to close this loop because you remember I made this assumption that there are these correlators for which I assume some power law, and there has to be a self-consistency condition, which I haven't talked about. I completely ignored that. So we have to close that loop. We have to like impose those self-consistency conditions. And those self-consistency conditions, if you recall again, are these R and Qs, which were related to the electron and spin correlators. And so in the form that I had written, this D minus 1 and R plus 1, essentially these correlators corresponds to 2 minus epsilon and 2 minus 2R bar in this new small variable language. And now you just have to equate eta S result, which is epsilon, to 2 minus epsilon to impose the self-consistency, and 2 minus 2R bar to 2R bar, which was the exact result for eta S. And if you close this loop, you exactly get the value that epsilon and 2R bar has to be exactly 1, meaning that your spin correlator goes as 1 over tau, and the electron correlator also goes as 1 over tau. So this is the SYK result that we have been looking for or anticipating. So meaning that at this non-trivial fixed point, which is the stable fixed point, and that's really important, you find that the the spin correlator has the SYK form, marginal behavior for the spin correlator, and the electron correlator has this 1 over tau behavior. So now coming back to your question, so when you're asking in the beginning, this is precisely what I was saying. So in this problem, you immediately see that, so the electron correlator is Fermi-liquid like, it's 1 over tau. But the spin correlator is not 1 over tau squared, but it's 1 over tau. So this clearly says that there is like no electron quasiparticle or anything, and there is a marginal behavior. And I mean, here it's even more exact because we have an exact result for the exponent, and it's in this SYK universality class. So now what I showed you until now is essentially at this critical point. So we tuned our system to this critical point and performed this renormalization group and showed that this critical point had this property that the correlator was SYK-like. And there's a nice physical picture that at this critical point, essentially all the 3 levels that you have in the system, they are nearly degenerate. And then you can ask the question, what happens when you go away from this critical point? Because that's the important thing, right? We want to dope the system and look at what happens at high doping and at low doping. So a very nice physical picture to see this is that at high doping, your hole-on energy is less compared to the spin-on energy, and then you can condense this, and this is how you would get a Fermi liquid. And so your charge carriers are 1 minus p, and modulo 2, it's basically 1 plus p. At low doping, the spin-ons have lower energy, and you make them as bosonic, and you condense them, and that's why you can get some magnetic ordering, like glassy behavior. You freeze these spins, you put them into some fixed value, and your charge carriers have now density p. These are just the holons, which are now fermionic operators. So this is how the schematic phase diagram we anticipate from this renormalization group theory that we have done, that we solve for this critical point, and then we roughly know by arguments like what the low and high doping phases are. And this is what the cuprate phenomenology, if you recall in the beginning that I mentioned, that you have low doping phase with charge carrier p, high doping phase with charge carrier 1 plus p, separated by a quantum critical point with SYK-like property. And the important thing is that it has been shown, so this is not my work, but people have shown that for this type of systems where you have this SYK criticality, there is a time reparameterization symmetry and certain other arguments by which you can show that the resistivity is indeed linear in temperature. So then we know that this critical point that we have found indeed gives rise to a phase at high temperatures with a linear in T resistivity property. So so we then capture the fundamental properties that you have this critical point with the strange metal emerging from it. So that's the main statement. Yep.
So you had shown from the experimental data orbital divergence specific.
Yeah, that's a good question. So here in this theory, we cannot.
Can you repeat the question, please?
No, I was asking in the experimental data, he had shown that there was a logarithmic divergence in the specific heat at the critical doping point. So I was wondering if this is also coming
So
up.
that's a tricky business, but that's a good question. So in this model, we cannot really prove that it's like T, it has to be like T log T. It has some divergence, of course, but it's not exactly T log T. But that is slightly slightly ambiguous thing, because even in experiments, I guess sort of that it looks like T log T, because that's the general belief that it has to be T log T, because people, when they write some marginal Fermi liquid theory, you get T log T, but it's not absolutely clear that it's T log T. So, but yeah, I cannot make like an absolute agreement for the specific heat in this case, like from our model and from the experiments. Yeah, but good point. Yeah. So this is the general picture. And then in the interest of time, I will skip over the large M version of this model, because I will be talking about this in detail tomorrow again. So what I will instead show you is that even numerically, people have solved this TJ model using DMFT and other techniques. And you see that the phase diagram is roughly what we get, that there is some deconfined critical point with SYK-like criticality, with some low doping spin glass and high doping Fermi liquid behavior. So in this sense, it's consistent. So until now, so let me switch the gears slightly. So until now, what I was talking about is a Mott insulator and doping a Mott insulator, where I had basically put the constraint that you cannot have double occupancy on any site. And this is a consequence if you imagine like writing a Hubbard model and you say that U is infinity, such that you do not allow like two particles on the same site. But then you can also ask the question, let's relax this slightly and not make like U infinity, but some positive number large enough. And then you can ask the question whether there can be like, so in particular, if you are at half filling, you can have like a metal insulator transition as you tune your interactions like from slightly lower value to higher value. So this is also something that we investigated. So here on the y-axis is 1 over U. So, and on the x-axis is doping. So what I talked until now is this U infinity limit, meaning 1 over U is 0. And I talked about doping this Mott insulator here. So this was the x-axis, and you find this SYK-type critical point. You can also solve this problem at half filling, but now instead of U infinity, you tune your U to some finite value, and you find a metal insulator transition. So this is an insulator at large U, but at small U, it will be a metal, because you can have double occupancy, the electrons can hop freely, and you have a metal. And we can show, and this was actually inspired by some previous numerical work where they also found SYK criticality for this kind of a metal insulator transition. And we also worked out a renormalization group theory for this point, and we also find consistent SYK behavior. So in general, the phase diagram for this Hubbard model, let's say, would be if you have this 1 over U here and doping here, then there's a line of critical points here. So it's a critical line with this SYK-like behavior, where you have this metallic spin glass in the small doping or like large U limit, and some disordered Fermi liquid at large doping or small U. Apart from this, we also looked at another problem.
So there's a marginal operator, that means that takes you away from all along that flow, or
no, I mean,
there's meaning that is that an exactly, that line is critical line?
Yeah, I mean, this is a schematic. So we believe that we haven't really worked out for some finite U and some arbitrary doping what it should be, but this you can actually prove from the renormalization group that we have worked out that the doping, like the boson density that you have, like the doping density, the criticality is independent of that. So you can also tune the boson density and you can still have like SYK behavior. So that's why we anticipate that you can have this critical line that connects this P equals 0 point at some finite U and infinite U and some critical P value. Because
So
there's a tunability in your boson density.
Okay, so that that operator is in some sense acting like a marginal operator,
Right?
Right. That it's sorry. Right. I mean, you're expanding around 1 over u. I mean, so it's right. You're doing an expansion around u equal to infinity. So it's not quite HU, I guess, is the operator. I mean, it's there's some.
Yeah, I mean, it's basically related to some hole-on operator essentially that will take you along this line. So it's I mean, it's a combination of both. Sorry.
The chemical potential is also.
Yeah.
Okay. From that fixed point, but he was starting from the lower fixed point.
It doesn't matter where you start.
Right. Yeah. But you had analytic control over there, and so I was just wondering what you can say in the vicinity of that fixed point when you go along.
Yeah. So
along
we
the
cannot
critical.
exactly work out. Let's say if I go along this axis or this axis.
No. I meant sitting at the critical point there on the x-axis. You move up along that line. Yeah.
So instead of looking this as a perturbation in like 1 over u or something, what you can think of is that you solve this problem at u equals infinity, and you have some chemical potential and some boson density, and then you solve this problem at some non-zero, infinite minus u or slightly finite u, and again like tune your chemical potential and boson density, and then you would get some fixed point with the same characteristic, but since the chemical potential will be slightly different because it's a U-dependent quantity, you will get slightly shifted value of this doping. Yeah.
Can I ask a question, please?
Yeah.
I mean, since this criticality is described by the standard SYK model, there must be some marginal operator actually in this theory that enables you to, move along this critical line. I mean, how do you, that's what I would expect.
Along this critical line, yeah, I think it has to be one of the, the boson operator. Yeah, boson density, that's what I believe. It has to be that's the one that tunes this or takes you along this critical line. That's the doping. I mean, that's what is changing here. So that's the operator corresponding to something like B dagger B or something in this language.
I see. I was thinking in terms of the low energy degrees of freedom of the SYK model, whether there is a formula for the marginal operator that does this job. I mean, that's what I was asking. Actually.
I see.
Yeah.
No, that I believe, I cannot derive, or I don't have a good handle on that. Yeah. Yeah, but good point. I can think about that. Yeah.
Okay. Thank you.
Yeah, thank you.
So Darshan, is your conclusion, have I understood your conclusion clearly? I just want to confirm that. So you are suggesting that at half filling the Mott transition, its critical properties are the same as the the projected U at finite doping. That's what you're suggesting.
At least if you look at the spin correlator, yes. I don't know about all the other operators. For the spin correlator, it's SYK-like.
I see.
So
one has to be
slightly careful. So maybe you can ask, let's say, density-density correlator. Is it the same exponent? I don't know. It could be different.
No. If you stretch that argument qualitatively, then if I think not scale U, but scale temperature, and go at undoped system to temperatures greater than the Mott gap. This is of course not a physics question because you can't, that's a huge temperature. But suppose you mathematically do this. So you will go to the where you are above the Mott transition essentially. So you're saying that physics should be roughly connected to the physics at zero temperature at
Yeah, could
That's
be,
what,
at least in the sense of the spin dynamics. But yeah, there might be some other physics that might come across. But then the point is, like, if you really stretch this argument, the point is that like if you introduce now the temperature axis, then there are other complications of this pseudo gap and other phases that kind of take over at large energy scales. So that they might like completely kill some of the physics at high temperature, some of this physics. So that I'm not sure of, and probably that is happening because the experiments observe pseudo gap and other stuff.
So now, is this still on the mean field theory, or is it now in a lattice when you talk
No,
of
this
this?
is still all this fully
mean
connected.
field theory.
Yes.
But what does it mean to have a metallic insulator transition on in a mean field theory? Because there's no lattice, right? So what do you mean by?
Yeah, that's a good question. So of course, if you like strictly stick to all this zero-dimensional thing, there is absolutely no meaning of like what is conductivity or resistivity because there is no lattice. But as I said in the beginning, like there is a connection at some mean field level between the things that I'm talking about and a square lattice DMFT approximation. So what you can do is you can calculate the resistivity or conductivity in a similar model on a lattice. And people have done that, let's say either on a Bethe lattice or on a square lattice, and you can calculate the conductivity of a model with exactly the same properties. And there you can make certain very quantitative statements. So here, of course, like purely in all-to-all, there is just, you cannot calculate.
Okay, but here, how do you then say metallic or insulating?
Is based on the fact that whether you have some, let's say, condensation of one of the holons or the spin-ons. So for example, if you, I mean, it's more qualitative in the sense that at small u, you have a hopping dominant phase, where you have electrons hopping and doubly occupied states are allowed. So in that sense, like you can really have some metallic nature, whereas in the insulating phase here, you really have like frozen degrees of freedom that these electrons simply cannot hop. Yeah.
Compressibility, right?
Yeah, okay, compressibility is another thing.
One is a compressible phase and the other is a rigid phase.
Yeah. So yeah, sorry. Okay, so then one another problem that we looked at is at small u, but at half filling. And this is an interesting problem that was motivated by experiments. So at large u, of course, you had Mott insulators. Mott insulator, at small u, you have some metal. At negative u, you have an attractive interaction, and so you can have a superconductor. So it turns out that instead of a direct transition between a superconductor and a metal, you can have a phase which is another non-Fermi liquid, which is called a failed superconductor or anomalous metal. And the property is that its resistivity is very small, but it's not zero to make it a superconductor, but it's much smaller than a Fermi liquid. And it has also some interesting properties, so this work was essentially motivated by a set of experiments that people had reported in two-dimensional disordered superconductors, where you can see that the resistivity, you have a clear superconducting transition, but then for certain tuning parameters, it can magnetic field or interactions or some gate voltage, the resistivity kind of saturates at some small value. So I think some of the curves are not absolutely visible, but there is like a resistivity saturation at some slightly lower values, much lower compared to the metallic or Fermi liquid value. And
what controls this residual value?
Sorry?
What controls this residual value?
It's basically the absence of quasiparticles. So that's what we show, that there is really a transport by some like pair fluctuations, and there is a Bose metal kind of phase that actually controls this residual resistivity in this case, and it enhances or reduces the resistivity compared to the Fermi liquid. So there is a transport by these pair of electrons. So these are not, so there are these fluctuating pairs which actually do not completely become coherent and condensed to give you superconductivity, but nevertheless they contribute to transport alongside your electrons such that you have like enhanced conductivity in this phase.
So can then one think about this as a pair fluctuating superconductor?
It's not a superconductor.
No, pair, phase disordered.
Yeah, but it's also, strictly speaking, not pair fluctuating, because if you, let's say, again...
phase disordered, I used the wrong word.
Yeah, okay, but still that's slightly tricky, because this phase is really without quasiparticles, at least the model that we consider. So it's, again, like using this SYK type of model with random and all-to-all, and this is really a system without quasiparticles. So you cannot even probably think of it like really a pair fluctuating phase that people try to describe in this high TC context. I mean, there's a whole bunch of literature on this, and I think people have tried that approach, and it seems to not really work out for this anomalous metals. Yeah, but I would be happy to talk about this later. So yeah, there are some ongoing works about this superconducting transitions as well. So essentially, let me finish quickly by saying that the entangled phases of matter that I've been talking about, and in general that you find in nature, they are a result of interactions and disorder. This is what I talked about today. But then there's a whole different branch and aspect to it, which is topology, which I haven't talked about today. But these are like kind of the three pillars of this highly entangled phases of matter. And usually the interplay between interactions, topology, and disorder, they give rise to these very exotic and interesting phases of matter. So just to give you a glimpse of what's happening currently in the field, so there are many interesting systems which are called these moire systems, where you stack like 2 layers of graphene or some other materials, and you twist them and you get a super lattice which has a very large unit cell, large distance between the sides. And they form a moire superlattice at a and at some special angles. They have an interesting phase diagram where you have some correlated insulators, some superconductors. So basically very much like a cuprate phase diagram. And apart from this, they also have very like presence of many interesting topological and magnetic phases, which are completely like not completely resolved yet. And so these are kind of open problems in this highly entangled phases of matter, which is emerging in like last 2 or 3 years, which are interesting to solve in coming years. So one of the things, again, of interest apart from these topological phases and exotic magnetic orders is also a presence of strange metal again. So just like in the cuprates, there's also a strange metal and non-Fermi liquid behavior in these moire systems, which begs understanding, and this is one of the open problems in this field. Apart from this, of course, there are quantum spin liquids that I mentioned at the very beginning, which have these characteristics of bulk fractional excitations and deconfined gauge fields. And as I mentioned, one of the most important challenge here is like really a smoking gun signature for these quantum spin liquids. And recent years, people have started realizing these quantum spin liquid states in cold atom setups. And the advantage there is that you don't have disorder, so that at least one complication that comes in real materials is kind of gone, and you have just an interplay between interactions and topology, and you have a good handle on that in this cold atom setup. So this is something I have started working on and would like to work in future to like understand better how these systems could be realized in cold atoms. And the other ambitious thing is actually like study the impact of disorder on this quantum spin liquid. So that's really at the heart of this physics, I believe, because all real materials have some randomness and disorder. And ultimately, I think if you really have to make some quantitative predictions or really want to understand if a given material is quantum spin liquid or try to put it to use once it is realized, it's really important to understand the impact of disorder. And in recent years, it's also been kind of realized that you may also have some disorder-induced phase transitions out of the spin liquid, or you could stabilize certain spin liquids by inducing certain disorders. So this is kind of an open problem that I'm highly interested in and thinking about in recent years. And I think it would be an interesting avenue to like pursue in the future. So that's one of the key open problems in this field that have been hanging around. And of course, there's a whole lot of other dimensions that I'm completely not talking here in the interest of time. But let me just summarize my talk by saying that I talked about this random TJ model, where I showed that it successfully captures at least the basic phenomenology of the cuprates. And I also showed certain short snippets of examples where you can apply SYK-type physics and build some theories where you don't have quasiparticles. And in general, you have these highly entangled phases arising from the interplay of interactions, topology, and disorder, and a comprehensive understanding of these phases is an open challenge. And as an aside, you can also have applications of some of these phases in some quantum communication or quantum sensor devices, especially some topological states. And in fact, not just these quantum spin liquids, but even on an elementary level, you can have certain systems where you have some topological excitations and some edges where you can build some spintronic devices that are topologically protected. So that's something, yeah, for the future. Thank you.
Yeah, I think the floor is open for questions.
Hi. So, sorry, again, back to this gauge fluctuation thing. So you had the temporal fluctuations, which you could incorporate using the time dependence of your lambda. So what is the effect of that on that critical point that you discussed?
Yeah, so that, so the lambda that we introduce as a Lagrange multiplier for like taking care of this constraint. So there is a whole bunch of technicality that goes behind it, how to really handle this. And let me put it like in a short form, what happens is that you have to take the limit of lambda going to infinity in this particular problem to actually like make meaningful statements about your observables. And the reason is that, so this chemical potential, so essentially what you are doing is some loop calculations and you have some wave function renormalizations. So, so for this particular problem, since you have this chemical potential, what you have to essentially do to get your physical observable O is you calculate your physical observable as a function of lambda in your partition function where you had lambda before, and then you of course divide it by the partition function, and then take the limit lambda to infinity in the end. And the reason to do this whole jugglery is that you can show, I mean, people have shown this in the Kondo physics literature, is that this limit is well defined in the sense to control the wave function renormalizations that you get. So if you put lambda to infinity, you can do this order by order calculation in a more systematic way such that some internal loops are suppressed in this limit lambda going to infinity. So that's why you send this lambda to infinity. Yeah, in this problem.
Sorry, I think my question was that temporal fluctuations of lambda. That's like the temporal fluctuation of the gauge field.
Lambda is static. Okay, so yeah.
The temporal fluctuations of lambda is like the temporal fluctuations of this gauge field.
Right, but here lambda is static, so that's what I'm saying. So here we set lambda to a
yeah. So do you know what happens to the critical point? Is the temporal fluctuation relevant?
No, that's beyond like to make any like controlled statements. Yeah, I agree. It's an interesting question, but I simply don't have the machinery to really tackle that problem. Yeah, but that's a good question. But yeah, it's really something very technically challenging that I'm not really sure about how to do it.
Even the large N.
No.
Yeah, you had this picture where you had the interactions, disorder, and topology. What exactly did you mean by topology there?
So it could be either band topology or some topological order where you could have some emergent gauge fields and so on. So like in spin liquids. So there are like, I agree, like there are different avenues from topology. So one avenue in the context of spin liquids would be like some emergent gauge fields and so on. Another avenue that I personally invested myself quite a bit was just like the fermionic systems where you have some topological characterizations and things like that. You could also have topological characterizations of excitations of some magnons or magnetic systems. And this is another type of topological materials. And these in particular may have like spintronic applications. So this is what I had in mind. So there are like three aspects that you can roughly divide it into, either like the topological order, or like the trivial topological insulators and superconductors, or these topological magnets. And yeah, so there are several subfields.
But if it's topological order, I won't distinguish that from interactions, right? Because it's the interactions that give you the
right. So they are intermixed. Yes, exactly. Yeah, I didn't draw this correctly.
Yeah.
I mean, they are separated, but there are of course an interplay between them. Surely, yeah.
Yeah, it's sort of a general question. Are there any systems one can realize where uh, this critical point or strange metal phase is realized without the superconducting, without being hidden by the superconducting dome, so that you see the strange metal phase just go? Is there anything one can rig up or do? I mean, why is it always associated with the superconducting?
Yeah, that's a good question. But I don't think there is really any real system where you like realize this SYK like critical point in isolation without any other distractions. At least I'm not aware of any.
But
particular
the converse, namely, there's nothing preventing it, right? I mean, nothing. Is there anything in principle that prevents it?
Not really. You need really the correct setup. So at least, for instance, you do have systems where you have a transitions from like this low doping with density P to 1 plus P. So there are plenty of systems that do that. So one example is like FL star to FL transition, where again you have some phase with a small Fermi surface and a phase with large Fermi surface, and you have a phase transition between them.
But that critical point doesn't lead to a strange metal.
SYK criticality. Yes,
yeah.
Exactly.
So you want the SYK criticality, but and leading to the strange metal.
Yeah.
Okay.
But so can I just comment
Sure.
more? So that's actually the interesting thing that I've been thinking about, but haven't been quite successful, is that so it seems like the ingredient to get this SYK kind of criticality is really this all-to-all connection. So that's the dream. Can you get this SYK correlator by not having all-to-all connection, but on really a lattice? And that's something I've been thinking a lot, but it's not really very easy to get that correlator marginal on a lattice. Even if you make like random interactions or random hopping, and if you restrict to like nearest neighbor or next nearest neighbor, it's not like very easy to get SYK type. Of course, unless you make some DMFT approximation and so on.
Yeah. And the other, just a small follow-up, is this strange metal phase. Of course, everyone talks about this linear resistivity in T, but are there other signatures which are very striking?
Yeah.
And
okay, that's actually a good question. So I did not emphasize on that. So one more thing, like a characteristic of this strange metal is a Planckian behavior. And that's why I think some people have started calling it as a Planckian metal, because the name strange metal sounds very strange. It doesn't really tell you what is happening, whereas a Planckian metal is a more apt name. And so the reason to call it a Planckian metal is that the resistivity, or let's put it in, so resistivity is proportional to T, but you can ask the question what the scattering rate looks like. And the scattering rate is usually like some constant KBT over some mass or E square and some other fundamental constants. And what has been shown experimentally, or that's the observation, is that this constant alpha is always 1 in the units of like h bar over E square and so on in terms of the fundamental constant. So it's really on a Planckian scale, the scattering rate. So again, that's why it's very exciting, because it's also connected to the SYK physics, that it saturates the bound that you can have on the length scale and the time scales in your problem. So it's really Planckian in that sense. So that's another hallmark of a strange metal. Yes.
Okay, so regarding this absolute last part of the talk, I couldn't understand this connection of the strange metal in Moire graphene, because I thought that one of the major difference with the cuprate strange metal and this Moire graphene strange metals are that this strange metallic behavior occurs at temperature scale which is larger than this, much larger than this flat band energy scale or microscopic energy scale, whereas in the cuprates, the strange metals occur much below the microscopic energy scale.
So I'm not saying that the model that I described has any connection to the strange metal phase in the twisted bilayer graphene. It was more like an outlook in saying that these are the open problems that one has to solve. But yeah, it has nothing to do with SYK or like the the model that I was talking about. It has probably some different physics that one has to carefully understand really what is going on in those systems. So I'm not at all suggesting that I'm planning to like apply immediately, or whatever I said immediately applies to that system.
Within your model, if you move away from the critical point, do you actually get the properties of the pseudo gap phase and the?
Yes, at least the spin at zero temperature, you get a spin glass, and on the high doping side, there is an interesting story that I will talk about tomorrow.
Okay.
Yeah.
Okay. Okay. Are there questions from the audience in the room or from people who are on Zoom? If not, then let's thank Darshan again.
Thank you.